This is Physics 1060, Descriptive Astronomy, Lecture 4, and today we're going to look at Chapter 4. So, light, together with related other kinds of radiation, such as infrared and radio, is almost our only source of information about the Sun and other stars. In order that we can use the information carried by light to the best advantage, we need to understand what light is and how it is produced. So what is light? Light is an electrical disturbance in space, a bit like ripples in a pond or sound waves. Unlike sound, though, light can travel through a vacuum. The velocity or speed of light in a vacuum is 300,000 kilometers per second, or 3 times 10 to the 8th meters per second. You need to remember this number. It's one of the most fundamental constants in nature. All electromagnetic waves travel at this speed in a vacuum. They can be slowed up a little bit when traveling through matter, but in a vacuum they all travel at the same speed. So a few more facts. It takes 8 minutes for light to get here from the Sun. So because the speed of light is so fundamental, we can use the idea of a light second or a light year as a measure of distance. The velocity of light is often given the symbol c for constant. The wavelength of light is the distance between crests in the wave. If I think of a wave as going up and down and up and down and up and down, the distance between them up and the next up is called the wavelength. And white light is a mixture of waves of different wavelengths. And as white light goes into a prism, for example, it splits all the different wavelengths up and gives us a spectrum. So visible light ranges from 400 nanometers, or 400 times 10 to the minus 9 meters, or 4 times 10 to the minus 7 meters. So 400 nanometers for violet light, and 700 nanometers for red light. So there are about 50 wavelengths of light across a single sheet of saran wrap. We often write wavelength with the Greek letter lambda. Now light is just part of a much wider range of radiation. It includes gamma rays, X-rays, ultraviolet rays, then visible light, then infrared waves, microwaves, and radio waves. Sound waves are not electromagnetic spectrum. We call them electromagnetic waves, and the range of radiation is called the electromagnetic spectrum. Radio waves are the longest, they could be up to several kilometers long, and gamma rays are the shortest. So, tuning a radio is actually selecting radio waves of different wavelengths or frequencies. All travel through a vacuum. And today, astronomers observe the sky at almost all accessible wavelengths of the electromagnetic spectrum. And as the following figure will show, some kinds of waves penetrate the Earth's atmospheres, like visible and radio waves, while others don't, X-rays and infrared and ultraviolet. You should know for the exam the electromagnetic spectrum and know which has longer wavelengths than the others. So this picture here shows the transparency of the Earth's atmosphere. And notice that the Earth's atmosphere is opaque to most of the electromagnetic spectrum. There's a window here called the visual window where light or electromagnetic waves in the visual range are transparent in our atmosphere. But infrared and microwaves, it's opaque. And again, there's a window of transparency for radio waves, which is why we use those for communication. And then it gets opaque again. This is really important because the Earth's atmosphere protects us from gamma rays and X-rays and most of the ultraviolet, which are harmful to our bodies. Now the frequency of a wave is how fast it oscillates in a second. And the unit is a hertz, which is the same as 1 over a second. So something that has a frequency of, say, 3 hertz means that it is going to pulse 3 times a second. Wavelength and frequency are related by the speed of light. So the speed of light is equal to the wavelength times the frequency, or c equals lambda f. For example, If you were listening to a local Christian radio station here in Nampa, KTSY on the radio, how long is the radio wave? Well, from our radio, we know KTSY is 89.1 megahertz, or 89.1 million hertz. I know that the wavelength then is c over the frequency. So speed of light is 3 times 10 to the 8th. This is 89.1. Mega means 10 to the 6th hertz. And so the radio waves are 3.37 meters long. So we can refer to a certain part of light spectrum either by its frequency or by its wavelength, since they're always related by a constant, the speed of light. The other thing about light is that these waves come in bundles, or sets of waves. We call these bundles photons. We don't notice the bundles with our eyes because they're so small and there's so many of them coming at us at once. But astronomers have sensitive enough instruments that we can collect a single photon at a time. And photons are particularly important when it comes to understanding the processes which produce radiation. Now, light and all electromagnetic waves are a form of energy. And electromagnetic waves are the major means of moving energy around the universe. And the energy of a single photon depends on its wavelength. So energy is hc over lambda. E is the energy of the photon, c is the speed of light, lambda, of course, is the wavelength, and h is called Planck's constant. It's just another fundamental constant that we look up in a book. So it's one of these constants of nature. You don't have to remember this equation, but there's a few things I do want you to remember from it. Long wavelength means low energy. Short wavelength means high energy. So the color of light tells us about the energy of the photons. Radio waves have long wavelengths, so they don't carry a lot of energy. If they're going through our body all the time, it doesn't really bother us. X-rays have very short wavelength. They carry a lot of energy and can damage the cells in our body. Now the next thing we need to talk about is temperature. What is temperature? Temperature is a measure of the random motions of atoms. So as the temperature of something rises, the atoms in it are moving or vibrating faster. There's actually a mathematical connection between the temperature of something and the random velocities of its atoms. We don't need to know this for the course. I just want you to know that higher temperature means higher average speed of the atoms in an object. So if this substance is a gas, the atoms move through space until they hit another atom or a wall. And it's the impact of the atoms on the wall that gives us something called pressure. Now in the USA, we use the Fahrenheit temperature scale, where ice melts at 32 degrees and water boils at 212 degrees. The rest of the world uses Celsius, or the centigrade scale, where ice melts at 0 and water boils at 100. But both of these 0 degrees does not mean that all motion has stopped. There's this idea of absolute zero is important, and that's the temperature when things stop moving, and it's minus 273 degrees Celsius, or minus 459 degrees Fahrenheit. So in astronomy, we're going to use the Kelvin temperature scale. It's an absolute temperature scale. It's based on the same distances between degrees as Celsius. So we obtain it by just adding 273 degrees to the Celsius scale. So absolute zero is written as 0 K. And then ice melts at 273 K and water boils at 373 K. The advantage of the Kelvin scale is that the energy of an atom due to its random motions is now proportional to the temperature. So now we need to examine some of the effects caused by changes in temperatures. So if I have a solid and I increase the temperature, the solids turn into liquids and the liquids turn into gases. And some solids go straight to a gas without going through a liquid stage, but we'll leave discussion of that to chemistry. So if the substance is a solid, the atoms are locked into place in a crystal and they just vibrate back and forth. So the higher the temperature, the more violent the vibration, until eventually they vibrate so much they start to break apart. That's when it turns from a solid to a liquid. And as these vibrating atoms shake them apart from the crystal and become a liquid, and they continue to vibrate more, have more and more speed, eventually they'll start to pull apart from each other, and that's when it goes from being a liquid to a gas. Now, liquids are rare in astronomy, so really in this class we only need to consider the differences between solids and gases. Now, at even the highest temperatures, the collisions are so violent that two atoms can knock the electrons off of each other and the gas becomes ionized. An ionized gas is sometimes called a plasma, and we'll deal with this more later. One of the important results of heating something is it gives off electromagnetic radiation. As we're going to describe below, by analyzing this radiation we can determine the temperature of an object. When a solid or a liquid or a dense gas is heated, it gives off a continuum radiation. The meaning of the word continuum is that the radiation is seen over a broad or a continuous range of wavelengths, not just specific wavelengths. So, an example is the glow that's given off of something that's heated up. It becomes maybe red hot and then eventually white hot, like the filament of a light bulb. And if I were to actually look at the light coming off of, say, my element on my stove as it warms up, it's not just red, it's lots of different wavelengths, and each wavelength comes in different intensities. The intensity is the amount of light of any given wavelength. And so if certain objects give off all these, we only see the wavelengths that are in the visible part of the spectrum. So, we sometimes refer to the spectrum of a hot, dense object as a continuous spectrum. Continuous spectrum, all wavelengths are visible. Now, continuous radiation from a hot body is given off over a range of wavelengths that depend on the object's temperature. Something that is perfectly efficient at radiating energy or light is called a black body. Doesn't mean it's black, it's just it comes from some of the modern physics terminology. So continuous radiation is sometimes also referred to as black body radiation. I really want you to know it's continuous radiation. The spectrum of radiation from a black body is described by Planck's law, named after the German physicist Max Planck, who first formulated the law in about 1900. Now, Wien's law tells us how much radiation to expect at each wavelength from an object at a certain temperature. We don't need to know the equation or write it down, but we need to notice the shape of the curve, that it has a maximum at some wavelength and fades away toward both long and short wavelengths. So something at 5,000 K, the intensity pattern looks like this. Notice that the maximum wavelength is in the orange. As I heat it up to 6,000 K, the maximum wavelength shifts to the green. Or at 7,000 K, the maximum wavelength shifts to the blue or ultraviolet. So then by looking at the max wavelength, there's a relationship between the temperature of an object and the maximum wavelength of light given off by that object. Now, a continuous spectrum looks the same whatever the kind of atoms the hot, dense object is made out of. It doesn't matter what it's made of, just its temperature. And the wavelength of the maximum emission changes with temperature, and that's Wien's law. Essentially, the maximum wavelength times the temperature is just a constant. So as you increase in temperature, you first get red hot, then white hot, then blue hot, though not very blue. So we can use Wien's law to measure the temperature of objects we cannot touch, including things like stars or pottery kilns. Wien's law applies not only to visible light, but to other electromagnetic radiation as well. We have lots of devices that use Wien's law. Pyrometers. Say I wanted to measure the temperature of a really hot oven. This object looks at the light coming off of it and tells you the temperature. Or an ear thermometer. As you stick this device in the ear, it looks at the infrared radiation coming off the ear and is able to tell us what temperature, or a forehead thermometer does the similar thing. So now we need to talk about atoms. Typical size of an atom is a little less than 1 nanometer, or 10 to the minus 9 meters. This would mean it would take several million to span a period on a piece of paper. Just remember it's very small. Now, an individual atom sort of resembles a miniature solar system in some ways. It has a nucleus, analogous to the Sun, with one or more electrons in orbit around it. The electrons are a bit like planets, except they're not really hard balls like planets. We think of it more as a cloud of electrons orbiting the nucleus. The nucleus has a positive electric charge, and the electrons have a negative electric charge. And electricity is the force that binds them together. The nucleus has most of the mass of the atom, but it's very small. Most of the volume of an atom is empty space that the electrons move about in. Now, if we examine a nucleus, we find it contains several protons. It may also contain some neutrons, but we're going to talk about those later. The proton is a particle that carries 1 unit of positive electric charge. The number of protons in a nucleus determines the atomic number and determines which kind of element or chemical element the atom is. Not the number of electrons. An atom can be ionized and have more or fewer electrons. It's always the number of protons that determines what the material is. So, for example, hydrogen has 1 proton. Helium has 2 protons. Carbon has 6 protons, oxygen 8, uranium 92. Every atom has to be made of one or other of these chemical elements. And there are 92 naturally occurring elements. There are a few more that have been made in physics labs, and we've organized them into the periodic table. So we have hydrogen 1, helium has 2, lithium has 3 protons, beryllium 4, boron 5, carbon 6, nitrogen 7, and so on. Understanding the structure of the periodic table is something you learn in a chemistry class. I just want you to remember that there are different atoms and they have different number of protons. The negative electrical charge on the electron is equal to the positive electric charge on the proton, and a neutral atom has the same number of electrons as protons. However, again, it's possible for an atom to temporarily lose or gain some electrons and become an ion. The nucleus is unaffected when an atom is ionized. It remains the same element. When an atom is not ionized, it is called neutral. An ion can revert to being a neutral atom by recombining with enough electrons to equal the number of protons in the nucleus. There are several ways of making ions. One way is in a fluorescent light bulb using electricity. Another is to heat gas so hot that collisions between atoms literally knock electrons off of each other. An ionized gas is called a plasma. Now on Earth we sometimes find material in the form of single atoms, but usually atoms combine together to form molecules, such as water, which is a combination of oxygen and 2 hydrogen atoms. When atoms form molecules, it's the electrons that bind together. The nucleus always stays distinct. The science of how elements interact with each other is called chemistry. The Earth's environment is particularly good for encouraging atoms to combine to form molecules. In astronomy, on the other hand, it's common to find atoms acting individually and not in molecules. It makes astronomy more simple. Now, most nuclei also contain 1 or more neutrons, and the neutron has almost the same mass as a proton but no charge. The most useful kind of helium contains 2 protons and 2 neutrons in the nucleus. We call that helium-4. Just means it's helium, meaning it has 2 protons, 4 meaning it has 4 actual objects in the nucleus. Now, a major difference between the solar system and an atom is that in an atom, an electron can only travel in certain orbits. Intermediate orbits are not allowed. The reason for this depends on quantum theory, which is one of the major theories of physics. So different electron orbits require different energies. And so on this figure, the distance of each orbit from the center represents the energy of the orbit in the electron. So the electron here can be in this orbit, it can be in this one, and 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 this one. It can't be in here. It's impossible. So to move an electron from a small orbit near the nucleus to a larger one requires you give the atom energy. So if an electron jumps from a large orbit to a smaller one, it has to give off energy. And the energy, either going in or out, comes in the form of a photon of electromagnetic radiation. Since the wavelength of a photon depends on its energy, only certain wavelengths of light can be produced as a result of electrons changing from one orbit to another. Similarly, only photons with certain wavelengths can be absorbed by an atom. Because of the importance of the energies of different orbits, we usually don't use the term orbit at all. Instead, we think of them as energy levels. These are the energies of the allowed orbits of an atom. Photons are produced and absorbed when atoms jump from one energy level to another. So for example, a photon of just the right wavelength, not any photon, it has to be just the right wavelength, can come in and strike this atom and hit that electron. That, if it's just the right wavelength, it causes the electron to jump up to the first excited state, or the next highest energy level. And eventually, it likes to be in the lowest energy level. It's going to fall back and it'll give off a photon. And one of the neat things is the light comes in one direction, it can go out in any other direction. Or a light, a different color, can come in and have just the right energy to bump the electron up to the second excited state. And then one of two things can happen. Number one, it could go right back down to the ground state and give the same color of light off. Or it could go from the second to the first and give one color of light, and the first to the ground and give a second color of light. And so I get very distinct wavelengths of light coming out of this gas. And we can analyze it and maybe be able to determine what's in that gas. Each set of chemical elements has an entirely different set of energy levels. So each element has its own set of wavelengths that it absorbs and emits. It's kind of like a fingerprint. We can identify a gas by the wavelengths it gives out. When an atom is ionized, its ion has different energy levels than the neutral atom, so we can even determine from the light coming off of a gas whether it's ionized or not. We can separate the photons of light coming out into their different colors using a prism or something called a diffraction grating, and then look at the light coming off. And this is the basis of the science of spectroscopy, which allows us to identify different elements in the light of distant stars. So for example, if I were to look at hydrogen gas and have light being given off by hydrogen gas, I get red wavelength, kind of this light blue and darker blues. Neon has lots of red. So if I look at, say, a neon light, I see it as red. Sodium has two strong lines in the yellow and pretty much nothing else, so a sodium light looks yellow. Mercury has this strong green in these yellows, and so a mercury light actually kind of looks yellowish green. We don't need to understand how prisms or diffraction gratings work. Don't worry about what makes the electrons jump up and down to higher levels. What I want you to know is the kind of spectrum we see here, where there are bright lines on a dark background, is called an emission spectrum. Generally, you get this kind of spectrum when you look at hot, low-density gas, such as in a nebula. If the gas density is high enough, or the emitting object was solid, we'd get a continuous spectrum instead, which we already talked about. So the spectrum of light from the sun consists of continuous emission, this continuous spectra, and looking at Wayne's law, it corresponds to a temperature of 5,800 degrees Kelvin. It has dark lines crossing it, corresponding to wavelengths of the transitions of various different kinds of atoms in the sun. The dark lines are called absorption lines, and that kind of spectra is called an absorption spectra. It occurs when light from a hot dense region, or continuous spectra, passes through a region of cooler lower gas, which absorbs certain wavelengths of light. So here we have the sun's absorption spectra. Notice that it kind of looks like continuous, and I get all the colors, but specific lines are missing. Those specific lines we can match up to certain atoms and be able to determine exactly what elements are in the sun or a different star. The absorption line spectrum is the third type of the three main types of spectra that we need to know in astronomy. A continuous spectra has all the different wavelengths. An emission spectra has only certain discrete wavelengths. An absorption spectra has all of them missing certain ones. This is an emission spectra of hydrogen. This is an absorption spectra of hydrogen. And notice that the lines that are missing are exactly the same as the lines that are there in the emission spectra. Now, the same region of gas can produce emission lines or absorption lines depending on the path of the light traveling for you. So, for example, if I had a white light and I had material above it, if I had a telescope and I was looking above it, the white light goes all different directions. The light absorbs only certain wavelengths, and as they are re-emitted by the atoms, they go in all different directions, some of them which will go toward your telescope, and you'll see the emission spectra. Whereas if I'm looking directly at the light bulb, as the white light comes off towards my telescope, certain wavelengths are going to be absorbed by gas, and as they come off in different directions, most of that probably won't be in the same direction, so I'll see missing light in that direction. When we look at the sun, that's what we're seeing, is an absorption spectra. So the three types of spectra to remember are continuous spectra, emission spectra, and absorption spectra. Now the next thing I want to talk about is the Doppler effect. If an object is moving towards us or away from us, the wavelength of the radiation will be changed by the Doppler effect. And you can see this or hear it with sound as well as light. So for example, if you ever have listened to a police car go by, as it's coming towards you, you hear one pitch in the siren, and as it goes away, it goes down. Or that sound you hear as a car goes by really fast. It starts off at one pitch and changes as it's going away. So as something comes towards you, it has an effect of bundling up the wavelength so it sounds higher pitch, or moving away is lower pitch. So as wavelength of light becomes longer, it's called a redshift. And that happens when things are moving away from us. If it's moving towards us, it's blue shifted, or the light's shifted towards the blue end of the spectrum. So this figure shows, if I have two observers here, and the source and observers are at rest, no matter where you are, you see the same wavelength, because as the pulses of light come out, the wavelength or the crests are the same wavelength as they come out in all different directions. But if the source is moving, this large object is centered around number 1, the second circle is centered around dot 2, the third circle around dot 3, the fourth circle around dot 4. And as the light's coming off, if it's moving away, the wavelength appears larger, so that we call that redshifted. Whereas the source is moving towards you, the wavelength appears closer together, and it appears blue shifted. So if we are dealing with sound waves, the pitch of something comes towards us is higher than that something that's moving away from us. The change in wavelength of the regular wavelength is equal to the velocity over the speed of the wave. So we can use the Doppler shift to determine the speeds of stars or galaxies that are even billions of light years away from us, determine how they're moving towards or away from us. Now this leads us to the 4 ages of astronomy. Up until Galileo, all observations were done with the naked eye only. So the ancients, the Greeks, Kepler, Tycho Brahe, all did their observations with the naked eye. And once the telescope started to be used, a new era of discovery of nebulae, of galaxies, and other celestial objects began. That's the second age, the simple telescope. The third age is photography and spectroscopy. So from Galileo to World War II, the telescope was used by viewing through it. So beginning around World War II, photographic cameras were beginning to replace the eyepiece in telescopes. So by exposing for long amounts of time, new objects were observed in the sky that were too faint to be seen by eye, even with a telescope. The fourth age is more recent, where we've started to look at the sky in other electromagnetic spectra. So other instruments begin to be used, instead of just a camera, to observe the sky in all electromagnetic spectrums. So what's the future? Probably going to be dominated by things like automated surveys. I look at the sky, I look at the same sky again a little bit later, I look for slight changes, and be able to determine how things are changing in time. And we need to understand a telescope a bit. So the first thing we need to understand is a lens. A lens is a curved bit of glass that bends light rays to a point called the focal point of the lens. And it happens because light travels slower in gas than in air. So as it goes across the surface, and the part that hits first slows down first, and it actually causes it to bend, and we can get the light then to focus down on a point. The first telescopes were refracting telescopes. They consist of two lenses, an eyepiece, and an objective lens. The objective lens is what focuses the light down from whatever I'm looking at, and the eyepiece changes it so that it focuses correctly on your retina in your eye. Now, this was the design of Galileo's telescope. However, his was very small. There's some problems with refracting telescopes. The first is they're usually very long tubes that are hard to keep stable. But more importantly, they're susceptible to chromatic aberration. Different wavelengths of light bend slightly more or others, and it usually depends on the wavelength. So the speed of light in glass depends on the wavelength of the light. So in this case, white light comes, the violet light is going to focus at a slightly different place than the green and the red. And so no matter how I'm looking at it, if I get the green light in focus, the violet and the red will be slightly out of focus. So telescopes improved dramatically with the invention of the reflecting telescope. It uses an eyepiece lens and a mirror. The first reflectors used spherical mirrors, but they didn't focus well due to a phenomenon called spherical aberration. That light that strikes different parts of the mirror all crosses at the same time. It doesn't matter what color it is, it'll focus here, but different places focus at different locations. Therefore, I get, again, a blurriness due to the spherical nature. Now, if I make my mirror in the shape of a parabola, the parallel light rays all strike at the same point, and I don't have any aberration. So good reflecting telescopes have a parabolic mirror. There are several kinds of reflectors. The first was invented by Newton, and it's called a Newtonian reflector. It has an eyepiece along the tube, a small mirror at 45 degrees, takes and bends the light out here, so the light comes in, strikes the objective mirror, that causes it to come into focus out here, but this mirror bounces it back to focus here, and as it goes through the focus, the eyepiece refocuses it on the eye of whoever's looking at it. Another type is called the Cassegrain telescope. It has a second curved mirror that focuses the light through a small hole in the back of the objective mirror, so that the eyepiece is opposite the opening that you're looking through. This is the type that's most available today. In general, the bigger the mirror, the better the telescope. But big mirrors are very hard to make. Until recently, with laser optics and modern machining technology, the telescopes are very expensive. A bit of word of advice. If you decide to delve into amateur astronomy at some point, or going to buy a telescope for a friend or family member, remember this. Don't waste your money on a cheap refractor. This is the $99 telescope at Walmart or different other places. They're hard to use and are generally more frustrating than enjoyable. Good reflectors are not that much more expensive and are well worth the money. a good reflecting 5-inch reflecting telescope might only cost you a couple $100s. A good telescope today no longer needs a special mount, but has a computer-controlled movement that most of the visible objects are programmed in, so you don't have to read up and try to figure out where things are. You can just enjoy looking at the stars. Now, modern professional astronomers no longer do any optical viewing. Very few eyeballs go up against telescopes. Modern telescope has a camera, which is, for the most part, is electronic. More than half of all observations by professional astronomers are spectroscopy, so looking at the parts of the spectrum that are emitted by various celestial objects, not even trying to form an image, just looking at what different wavelengths of light come off the object. Now, one of the problems with looking at the stars is we're on the Earth, and it tends to move. So, with the Earth rotating, one had to constantly keep moving your telescope to keep the object you wanted in view in the field of view, or the area of the sky your telescope could see. All sorts of mounts were designed to aid this process. This is actually Newton's telescope, and he had a little wooden ball that it sat on, and literally you would have to keep the object you're looking at in the telescope by moving it with your hands all night. Now, there was an invention called the equatorial mount, and it allowed an astronomer to keep the telescope pointed in one place for a long period of time. Essentially, you took your telescope, you took the axis of your mount, and it pointed towards the North Pole, and then you put a clock on it, and so that the axis turned at the same rate as the Earth turned, and that way, even if you're looking off at a different direction, the telescope would be turning and would always match the rotation of the Earth. A properly aligned telescope with an equatorial mount can hold a star in its field of view all night long. And the other thing we have to consider with telescopes is where we are going to set up our observatory. For best viewing, you need a clear, dark, dry, smooth air sky. Professional telescopes tend to be built in low latitudes so that more of the sky is visible at any time. So international cooperation for major telescopes is a must today, and many of the big telescopes are actually owned by several countries. Now, radio telescopes are used by professional astronomers and look nothing like optical telescopes, but use the same principles. We have this large reflector here, which acts like the mirror at the back, but it reflects radio waves, not light waves. And the eyepiece instead is some instrumentation at the focal point. This is pictures taken at the National Radio Observatory in Green Bank, West Virginia. This radio telescope is 480 feet across. You can see the semi-truck down here. It gives you an idea of how big this radio telescope is. Now, if I want to look at infrared light, we have flying aircraft high in the atmosphere, and it can observe the infrared regions of light spectrum. The telescope generally has to be cooled with liquid nitrogen, so minus 320 degrees Fahrenheit. All objects emit infrared light, even the telescope, so we have to cool it down so that it's dark, and we can see the infrared and not have the infrared being given off by the telescope body itself change what we're looking at. Of course, we also have telescopes in space. The most famous is the Hubble Space Telescope. And it was built to avoid the atmosphere, but today we can actually do a little bit better with the invention of adaptive optics. However, it's still the best way to observe in the ultraviolet region of the spectrum. Generally, atoms have lots more transitions in UV than the visible, so therefore it gives us some idea of which atoms are present in the object being viewed. The science of understanding what elements are present from the light emitted is spectroscopy. Space telescopes are the best for infrared, for ultraviolet, for X-ray, and gamma ray light regions. And this is the end of Chapter 4.